In this tutorial I show you how to create this fractal glass distortion effect in Three.js. Make sure to stick around until the end to get the code and textures I use in this video. Also make sure to check the chapters in the video timeline. I started seeing a trend of people using this kind of glass distortion effect as a design element in Photoshop and wondered how to implement something similar in Three.js. For this effect we use a texture as a displacement map. Based on the different color channels in the texture, the pixels of the affected layer below are moved on the x and y axis away from the original coordinates to create the distortion. In Photoshop this is really easy. You simply go to Filter, Distort and then Displace. There you determine the maximum distance the pixels can get displaced and a PSD file which acts as the displacement texture. You can do the same in the free online Photoshop alternative Photopea as well, but I'll cover that in a future tutorial. We don't have such a displacement option in Three.js, so we have to write a bit of code to get the same effect in our live renderings. Fortunately, this is not too difficult either, so let's jump into the code. As a starting point, I use one of my daily Three.js projects, which you can find on CODEPEN and my Instagram account. Conveniently, these already use a post-processing setup, which we can utilize to add our displacement shader on top of the scene. I made tutorials here on YouTube going into detail about those scenes, so make sure to check them out to learn more about my usual Three.js setup. You can find the code to this and my other daily projects for free on CODEPEN. In the HTML part of our code, we simply add a canvas element with the ID canvas. This is where our Three.js scene will be rendered later. That is already all for showing the Three.js scene on our website. Of course, you can still add any other HTML element in addition to the canvas. In the CSS, we don't really have to do anything, but if you want to use a similar overlay as I'm using on CODEPEN, you can copy and paste that part of the code or adapt it to your liking. All the interesting stuff happens within the JavaScript portion of our code. Here we start by importing Three.js. Next we import all the other components we will need. I always use my gradient HDRs, which you can find on Gumroad and GitHub, to add some mood to the scene. For that we need the RGBELoader later. Then, importantly, we need the effect composer, which allows us to add the post-processing in general. To the post-processing we add the render pass, which we import next. Now we can import the ShaderPass, which we will use to create our displacement effect. The following components are not necessary for the displacement, but I tend to use them in most of my scenes to add some additional effects. Then I use the VertexShader to import my 3D model, but you may use a different loader if you're importing a different file type. Lastly, I import the orbit controls to let the user move the camera around. So far about our import statements. Now we can create a renderer and render our scene to the canvas. Then we set the background color, the pixel ratio and the renderer size. Finally, we create a new scene. In the scene we create a camera and position it. Here I also create the orbit controls. For this tutorial I will skip the orbit controls part, but if you're interested in learning more about this particular approach, let me know in the comments and I'll make an additional tutorial about it. The next most important thing is the HDR Equirect, which we use to add the gradient HDR to the scene and put everything in a colorful light. Make sure to check my tutorial about this on YouTube and have a look at the gradient HDR pack on Gumroad. I also covered the Three.js material with the surface imperfection that we are using here in another tutorial. The same is true for the FBX model import, so make sure to check them out in the original video. But now the interesting part starts. We create a new constant with the name render scene, which equals a new render pass that takes the scene and the camera. This will later act as our base layer on top of which we apply the effects. Now we can add all of our desired effects. For this scene I'm adding the after image pass and the Unreal Bloom pass, but you can also skip them or add other effects. This brings us to the constant displacement shader, inside of which we will create the most important stuff for the displacement effect. In order to understand what we are defining here, we need to first understand the principle of how we want to apply the displacement effect to Three.js. Generally speaking, I want to add the displacement to the entire scene and not just an object in the scene, so it makes sense to apply the displacement within the post-processing. In order to apply the logic of displacement as a post-processing effect in Three.js, we can utilize vertex and fragment shaders. These shaders use a specific language called GLSL, but we can still spell out the shader in our JavaScript file. In order to use this effect, you don't really have to understand the complexities of vertex and fragment shaders. Admittedly, I don't understand them very deeply either. You can simply copy-paste the code and I'll try to explain the most important values so that you can make some changes on your own. We start the displacement shader constant with a few uniforms. Those uniforms will be helpful in the fragment shader later, but they also allow us to change the specified values outside of the shader, which makes it easy to animate them, for example. We use tDiffuse to store the Three.js scene. Then we have displacement, to which we later add the displacement texture. Lastly, we have scale, which determines the strength of the displacement, and tile factor, texture, which defines how often the displacement texture is repeated. We can practically use this to resize the texture. This brings us to the vertex shader. Fortunately, we don't really have to understand what is going on in here. Generally speaking, the vertex shader determines what point of a 3D object is where in the three-dimensional space. However, we use a standard Three.js specific boilerplate code here, which allows us to connect vertex shader and Three.js. So this will almost always look the same in any Three.js context. Next we have the fragment shader, where the most important stuff happens. The fragment shader basically determines what color each individual pixel on the screen displays. So as we want to move pixels on the X and Y axis, you can already imagine that the fragment shader will be important for that. Here we start with two uniform sampler 2Ds, which allows us to use the Three.js scene and the displacement texture as inputs. Then we have the scale and tile factor that we defined earlier, and the varying vec 2 VUV, which we take from the vertex shader. As I've mentioned before, the vertex shader basically connected our Three.js scene to the shader. So we can imagine the VUVs to be the default coordinates of our rendered Three.js scene. Every pixel of the Three.js scene is still at their regular position. So the Three.js scene would look just as always if we would now simply let the fragment shader output the T-diffuse across all the VUVs. In order to displace them, we now know that we have to somehow move the VUVs away from their original position based on the displacement texture. With that in mind, we can start the void main, which calculates what we want to do with the pixels on the screen. In my case, I'm starting the void main with a conditional statement that checks if the UV coordinate on the x-axis is smaller than 0.5 and larger than 0, and if the UV coordinate on the y-axis is smaller than 1 and larger than 0. Practically, this means that we apply the displacement only on the left side of the screen. Of course, you can change the values to apply the effect to a different part of the screen, or you can cut the if and else statement altogether to apply the effect to the entire screen. Now we can start our displacement logic. We first create tiled UVs to allow us to repeat the texture and thus change its size. Then we define the vector disp as the texture of our displacement according to the tiling. By adding .rg at the end, we say that we are using the texture's red and green channels and multiply those by the scale. So to recap, we are creating a vector which gets its values based on the color channels of the texture multiplied by the scale. As we are using an image which has different color values across the texture, we can expect those values to be different than 0. So they are ideal to move the original UVs away from their position by those values. Thus we can now use disp as part of our distributed UVs. For that we create another vector, distUV, which takes the original VUVs and adds to it the disp, pushing the pixels away from their original position. To apply this to our screen, we have to set the GL color to the new texture, taking our original Three.js scene with the T-diffuse, as well as the distributed UVs with distUV. Now we have the else statement, which basically applies no displacement to the rest of the screen by setting the GL color as the T-diffuse with the original VUVs instead of the displaced UVs. And that's already the entire displacement shader code. But you might wonder where our displacement texture comes from. We didn't link to any file yet. For that we go to the next line, which sets the constant displacement texture as a new Three.texture loader, loading the displacement texture as an image file. Importantly, we set the min filter equal to the Three nearest filter. This helps when tiling the texture by preventing empty rows between the tiles. Now that we have the displacement logic and the texture, we can create a displacement pass. This is a new ShaderPass, which allows us to use the vertex and fragment shaders inside of the post-processing later. Thus it takes the argument displacement shader, in which we spelled out the GLSL shaders. This also allows us to change the shaders uniforms. Here we can now set the uniform displacement to the displacement texture that we loaded just a moment ago. Besides setting the displacement texture, we can also override the scale and tile factor here. To put everything together, we create a new effect composer. Here we first have to add the render scene, which acts as the base layer. On top of that, we apply the afterimage pass and the bloom pass. Then we can finally add the displacement pass. Keep in mind that it matters in which order you add the different passes to the composer. If you would put the displacement pass right behind the render scene and then the other effects, the effects would be applied on top of our displacement. In this scene, this doesn't make much of a difference, but in other contexts this might be crucial. So feel free to play play around with the order in which you add the passes to the composer. After the composer, we just have the orbit control logic, which I will skip over here. After that, we have a resize function in which we update the renderer and the composer size when the window size changes. Lastly, we have the animate function, which also updates the composer continuously. And with that, we have made it through the code, but make sure to stick around to get the displacement textures that I'm using here. During the process of making this tutorial, I created and tested a bunch of textures to see which works best in what kind of scenario. To let you follow along with the tutorial, I created a freebie pack with 2 textures that you can use with this code. I have also created a full pack with more than 20 unique displacement textures in resolutions from 1K to 4K as PNGs and JPEGs, including compressed versions for web use, as well as PSD files for using the textures as displacement maps in Photoshop. This is by far the largest and hopefully best organized asset pack I have created thus far, and it's a great opportunity to support my work, so please check out the full displacement texture pack on Gumroad and consider supporting me this way. A free way to support my work is to subscribe to my channel, like this video, and tell me what I should do next in the comments. You can also join our Discord and find my latest work on Instagram. Thank you for watching all the way until here, and I'll see you in the next one.